you see the top picture, I have on the left-hand side the two most famous formulae of 20th century physics. One of them, the second one I think, is Einstein's E equals mc squared. That tells you, c is a constant, it tells you that E, that's energy, and mass are equivalent. So energy and mass are equivalent. The top formula is even older, the beginning of 20th century physics, of quantum theory, was Max Planck's formula, E equals h nu. Nu is a frequency, that's the Greek letter nu. H is again a constant. So it tells you energy and frequency are equivalent. So if you put the two formulae together, it tells you mass and frequency are equivalent. So if you have a massive particle, a stable massive particle, it is a clock. It's a fantastically accurate clock. And a lot of the amazing things you can do in physics these days depends upon that fact. The fact that we have so precise clocks ultimately depends on the fact that mass gives you frequency. So that's the top picture. The bottom picture is telling you what would happen. You see, I've introduced, in addition to the cones, what mass gives you, and it gives you how clocks behave. So I've got two clocks whizzing through the point of the, you see, imagine you have two clocks whizzing past each other, very close to each other at that point, and they're identical clocks, but the first tick is represented by the first little bowl-shaped surface, the second tick is the second surface. So we now have the geometry of space-time if we don't just have the cones. I should say the cones, in order to describe the geometry, you need 10 numbers per point. The cones are given by 9 numbers. That's really the ratio of those 10 numbers. The 10th number is the scale. Certain things in physics only need those 9 numbers. Certain things need the 10 numbers. The difference is, if you have mass, then you need the 10 numbers. If you don't have mass, you only need the conformal geometry. You just need the light cones. You don't need the scale. And a lot of physics doesn't need the mass. And the main part of physics which doesn't need the mass is light. Photons have no mass, and in the bottom picture you see a photon going along the cone. It never even meets the first cone, the first bowl-shaped surface. So that the photons don't need the mass, they only need conformal geometry. So this is an important point in the diagrams that I want to describe to you. Now here is a little trick. It's just a trick, but it's an important trick. What I've done at the top is, like the picture we just had, the Escher picture, I've squashed down infinity so that it is a boundary. So the purple line on the left, well, it's at infinity, you don't see it. But on the right, I've squashed it down, just like in the Escher picture, to be that boundary at the top. So I've squashed infinity down, and as long as we're only talking about things without mass, it very well describes the physics. Now, in the remote future, the most of the particles that will be around, by a huge factor, will be photons. And the photons, we see the picture that I described here came about because I was worrying about the future, you see, and I'll explain a little bit about why I was worrying about the future. That comes on later, but let me talk about the beginning too. The Big Bang, I've done the opposite trick. I've stretched it out, and that is another boundary. So there's nothing unconventional about this picture. It's not usually drawn this way by cosmologists, but it's a perfectly reasonable way to draw it. Now, the point I'm making here is in the remote future, we have things with no mass, and so even the physics is pretty well described by this picture. And in the past, it's the other way around. You see, in the remote future, you have it very cold, very rarefied. In the remote past, in the Big Bang, it's the opposite. You have very, very hot and very dense, but in a certain sense, they're very, very similar. And if you didn't have mass, they would be extremely similar. And that's the important point I want to make. Now, you see, why do I say that in the remote past, near the Big Bang, it's good enough to ignore the mass? Well, it's a different argument. There, things get so hot, everything is moving around so fast that the energy in their motion is much greater than the energy in their mass. And so the particles are described very well by a particle which has no mass whatsoever, because the mass that it has is completely swamped by the energy in its motion. And so again, you can legitimately describe the physics by things with no mass. And so the picture is a good physics picture too. Now, I want to elaborate on this a little bit. First of all, in the past, now, you see, why does the picture not have that great mess which I described? That's a much more likely thing to be the beginning of the universe. Why do I say much more likely? Well, if the universe was chosen at random, it would be like that great big mess at the beginning, not just like the very nice smooth picture that we seem to see. Now, this is a feature of the second law of thermodynamics. Now, what does the second law of thermodynamics say? It says that randomness increases. Well, it's called entropy, which is roughly speaking a measure of randomness, and it tells you as that time progresses, randomness increases. Now, this then tells you that if you go back in time, the randomness should be very, very small. So the universe was not random. Now, this is a thing that people have trouble trying to come to terms with, and they try to make inflation get rid of all irregularities, but it doesn't. And I tried to say that in the earlier description. I don't think I should say any more about that much, but let me say something about this picture up here. Now, you see, as you go back and back and back in time, another way of saying the second law is that if you go backwards in time, things get less and less random. The entropy goes down and down and down. Now, what's the earliest thing that you can directly see? That's the origin of this microwave background, this radiation which is coming in all directions. It was discovered. It twice got the Nobel Prize. Once it got the Nobel Prize for its discovery. Secondly, more or less got the Nobel Prize because of this picture here. This picture is describing more detail what the radiation is like. It's telling you the bottom, we see the horizontal line at the bottom, the x-axis, if you like, is the frequency, and the y-axis going up is the intensity. And that tells you what you see in this radiation. And then you see these lines which are error bars, and these are exaggerated by a factor of 500. So you must consider that the error bars are hugging that incline. So it's a very good picture of what that radiation is like. Now, there's a bit of a paradox there, because what is this a picture of? This is the famous Planck curve, which describes, well, maximum entropy. It tells you what a state of maximum entropy, what radiation and matter in equilibrium with each other, the radiation would follow that curve. So what do we see? You go back and back and back in time, the entropy should be going down and down and down until the first point that you ever see, the entropy is at a maximum, because this curve is telling you it's at a maximum. And that seems like a paradox. I regard that as the mammoth in the room. Why don't cosmologists worry about that? Because it should be a state of very low entropy, whereas you see a state of high entropy. Now, it's not a paradox. Why is it not a paradox? Because what we are seeing is radiation and matter in equilibrium, and that's fine. Okay, the universe is expanding, but that's a minor point. That's not the point of the argument. The point of the argument is that what you're not seeing in that picture is the entropy being low in gravity. And this is a crucial point of the picture. Now, you see here, the top picture here, I just have a cartoon. Suppose you have a box and you have a gas in the box, and initially it's tucked up in the corner, and you remove the partition, if you like, and the gas then spreads out. So uniform state represents high entropy for a gas in a box. Now, what about the bottom picture? Now, these are gravitating bodies. You imagine, say, a galactic scale box, and these are stars or something. And then you see, you could start off with a uniform state, and as the entropy increases, it gets more and more clumpy. So what you're seeing in the universe is a combination of the top right picture and the bottom left picture. Uniform sky. This indeed is what you see. This microwave background is extremely uniform over the whole sky, which is consistent with low entropy in gravity and high entropy in matter. And that is what we see. So the puzzle that we've got to explain is, why was gravity not why was it sort of aloof to all this raising of entropy? Okay. Well, you see, it's important too, how we live, because you see, we live off the sun, and people say we get energy from the sun. That's not really correct. Schrödinger was first, I think, to point out what we really get from the sun is energy in a low entropy state. The sun is a hot spot in a dark sky, and because of Planck's formula, the energy comes to us in a small number of photons, and it goes away in a large number of photons. I don't want to talk about that picture particularly, but it's an illustration of we're living off the fact that the universe has condensed, and the matter in the universe is condensed into these hot spots, which are stars, and that's what we live off. That's how we our entropy is kept low because of the sun being a hot spot in the dark sky. So, okay, this is consistent with the picture I've shown you here, that the gravitational degrees of freedom are not excited. They're very uniform, and one way of saying that is in this picture. I had another complicated way of saying, which I won't describe to you, but my former student, Paul Todd, had a much better way of saying it, and that is just this picture. It's saying that conformally, you can stretch out the Big Bang and make it a nice, smooth boundary. That's not unconventional. It's not the way you usually hear it from cosmologists. It's a picture of the way the universe is. That's not unconventional. What is unconventional is my next picture. What I'm saying is that our eon, you see the one in the middle is meant to be us. That's our universe. I'm not calling it our universe, because our universe, I'm saying, is this continuing succession of eons. Our eon started with our Big Bang, and it will finish, in a certain sense, by this exponential expansion. And when we stretch out our Big Bang and squash down our remote infinity, we find that it seems to fit very well. The squashed down remote future does seem to fit very well to a stretched out Big Bang, with this very special condition that the universe was very uniform. And it gives you that. If this model is correct, then you have an elimination of all those very messy, complicated Big Bangs that might otherwise have taken place. So it's a very nice model, I think. And this is what I want to try and describe to you. So this universe, the universe consists of a succession of eons, each of which has its own Big Bang, each of which is very nice uniformly Big Bang, which is the continuation of a previous remote future. As I said before, they don't look very much similar if you think of the geometry which involves distances and mass, because you have a very hot, dense initial state in the Big Bang. You have a very undense, very rarefied, cold remote future. But from the conformal point of view, if you squash down the cold universe, it gets hotter. If you stretch out the hot universe, it gets colder. And so even the physics matches very, very beautifully.